Hi all, I am Arpita. I work as a research fellow at School of Computing, National University of Singapore. Prior to that, I have completed my Ph.D. from Indian Institute of Technology, Kharagpur. Today, I will be going to discuss my Ph.D. work here. But first of all, I would like to thank 18 ICDCIT Ph.D. Research Symposium for providing us this opportunity so that we can discuss our work here. Starting with the plan of the talk, I will start with the introduction where we'll see what is fault localization and the motivation behind this work. Then we'll discuss the basic concepts with the literature survey, and then we'll see the objective of our work and measures of evaluation. Further, we discuss the different four different proposed techniques, and then I will conclude. So, starting with the introduction, as we all know that with the increase in size and complexity of software systems, bugs are completely inevitable. So, whenever a software developer faces any program failure, first thing he tries to do, he tries to localize the bug. And for that, he actually has different automated bug localization techniques. And those bug localization techniques, what they do, they provide rankings to the statements based upon their suspiciousness of containing a bug. But the techniques which are already available in the market, those are not very effective and also not efficient. So there is a huge demand of automated bug localization techniques which are both effective as well as efficient. These are all what I will discuss. So, as I told, that bug localization techniques is the most expensive, tedious, and time-consuming activity during the complete process of bug debugging, program debugging. And with this increase in size of program and its with its complexity, their likelihood of containing bug also get increases. Therefore, to reduce the total debugging time, the fault need to be localized by searching very minimal lines of code, and the localization algorithm should be efficient. Now we will see some of the basic concepts. So first thing is coverage data and execution result. The coverage data shows that whether a particular program element is being covered or not. For example, if we take a statement as a program element, and this table will show the coverage data for statements. So we can see like these columns are representing the statements and test cases are represents the test cases. Okay, so this cell is showing that statement 1 is covered by test case 1, and here if we see that statement as e minus 1 is not covered by test case 2. And the last column shows the test case result, whether the test case is pass or fail. Pass or fail means successful or failure, like if the objective output is equal to the actual output, then we say that the test case is pass, and if not, then we'll say the test case is fail. Now coming to the virtual test suite. Actually, in virtual test suite, the test cases which presents are like they cover only one particular statement at a time. So practically, this type of test suite is not possible. That's why it is termed as virtual test suite. Now, these are some of the sorry, complexity metrics that we have used in our work, like cyclomatic complexity, strict cyclomatic, modified complexity. Max nesting shows the maximum level of control structure within an operation, count line code, and count path. Now, like what is deep neural network? We all know that it is a type of ANN with multiple hidden layers which maps input to the output by formulating a correct mathematical formulation. For example, it has just like classified the dog image as a dog. So now coming to other definition, that is agglomerative clustering. In agglomerative clustering, we cluster the initially we think that each of the element is a separate cluster, and step by step we merge two most closest element in a single cluster, and we continue this process until all the elements will not become in a single cluster. Kennel law correlation coefficient is a metric which help to determine the association between two different ranking sequences. And this is the example for that. Now coming to the literature survey. So basically, we have divided fault localization techniques into two different categories, like single fault localization techniques and multiple fault localization techniques. The single fault localization techniques are further divided into slicing, SBFN means spectrum based, machine learning based, and mutation based techniques. In actually, traditionally the slicing based techniques are used. Nowadays, only slicing is not used; it is actually embedded with different type of other techniques. Slicing is further classified into static, dynamic, and hybrid. SBFL techniques are formula-based techniques which takes the information of particular element is covered and not covered by how many failed and successful test cases, and using a particular mathematical formula it derives the suspiciousness of a statement. Now coming to the machine learning techniques, these techniques are further divided these fault localizations are further divided into two classes, like using the basic machine learning methods like SVM, decision trees and all. And the second one is the neural network based methods in which they have used different BPNN, RBFNN, CNN, DNN methods, and those are also divided into two categories, like only coverage based methods or further learning of those coverage based result methods. And here the multiple fault localization techniques are divided into basically three categories, like one bug at a time, like you fix a bug and then retest and you continue this process until and unless all the bugs are not located. In a parallel debugging, we just classify the test cases into different classes, like different classes based upon the number of faults present, and then we take those clusters of test cases and parallelly debug the program. So it is a fast method. And few other techniques like based on data mining and all are present that we have kept in an additional techniques class. So based upon this literature survey, we have identified few shortcomings of existing FL techniques, which are like those techniques are not too effective, especially for large size programs, and most of the existing techniques assign same suspiciousness score to multiple statements, which led to the problem of ties and which reduces the effectiveness of the technique. And also, the existing techniques do not address the effective fault localization at function level, and the efficient and those localization techniques are especially not efficient for multiple bug programs. So, in order to solve these problems, we have defined our objectives like this. Like we propose a statistical based method for effective fault localization. Then we also propose a suitable neural network based methods which will target the following these objectives. Like we'll try to increase the accuracy of localization method for especially large size programs, and to reduce the runtime of localization algorithm we use a hierarchical approach. Okay. And we define new metrics and concept for the hierarchical approach where we first localize the bug at function level and then at the statement level. So for the function level bug localization, the metrics we have proposed is function complexity metric, function execution ratio, and dependency ratios among the functions. And we also try to assign unique suspiciousness score to each of the program element. And we handle the programs with multiple bugs based on the clustering of failed test cases. So based upon these objectives, we have defined our proposed techniques, and the measure of evaluation that we have used is like exam score. Exam score actually measures the number of statements that has to be examined to find a bug divided by the total number of actual statements present in the program. And to measure the improvement of a technique with respect to another existing or any other technique, we have used RAMP, where the formula is given in equation 6. Now coming to our first work, that is FTFL. FTFL is Fisher test-based fault localization. Actually, most of the existing SBFL methods are formulated based on the experience of developers or software testers, their intuition or different heuristics. So we have proposed to use a statistical method to calculate the suspiciousness statements instead of using any experience or intuitive formula. So, since the chi-square test or d-test are not quite useful for different size programs, we have decided to go for Fisher test. And in the Fisher test, we have tested the null hypothesis that whether the program execution result is independent of the invocation of the executable statement as or not. Since the existing Fisher test, the actual original Fisher test is computationally very expensive, we have defined a modified Fisher test. So the notations that we have used in the Fisher test are like this, like tau shows the total number of test cases, tau p the total number of past test cases, likewise tau f. Tau cs shows the number of test cases that has covered or executed a particular statement. U shows not covered. Cp shows that covered by past test case. Likewise, the other notations are defined. And we have also created a cross classification table for each of the statement, where the four parameters are the most important, like whether the particular statement is covered, with how many pass or fail test cases that particular statement has been covered, or with how many fail test cases that particular statement has been not covered or covered. So these are the this cross classification table consists of these values, and we have created for each statement. Now the actual Fisher statistic formula is given in equation 7. But here in our main motive is not to derive the actual Fisher test statistic value. Our motive is to determine its value and to measure the relativeness behind different statements of containing a bug. So if we remove any such identity means variable which is common for every statement, so it won't affect the relative result. So the tau factorial, tau p and tau f is common for every statement, so we have eliminated remove those variables, and our simplified formula is this equation 8. And since we know that factorial is very computationally expensive, so to reduce the expense, we have taken the log of fs dash. So this logarithmic formula is given in 10, in equation 10, and then we have simplified this formula using basic log formulas, and this is our last logarithmic value of this uh, like this formula we have used. And then we determined whether the coverage of executor statements is correlated with the past test cases or failed test cases. For that, we have calculated the lambda p and lambda f, and then based upon the derived value for the modified Fisher test and lambda p and lambda f, we have divided the statements into five different classes, like the classes c1 to c5. Like class 1 statements have a high association with coverage, and they have high association with failed test cases. Means these class statements have a high probability of containing a bug. So based upon these values, we have then ranked these classes, like C1 is having the highest probability, then C3, C5, C4 and C2. And then we have calculated the psi s, if lambda f is greater than lambda p, then we take exact mod of that MFS. Otherwise, we take the if it is less than lambda p, then we take the negative of MFS. Otherwise, the value is assigned as zero, like neutral. Now, to validate the effectiveness, or to validate the effectiveness of our method, we have taken some programs and we tested this method. So the programs that we have taken are open source. They have taken from these two repositories, like Siemens Student, DefenseJ and NTS. So these are the characteristics: the number of faulty versions present, line of code, number of function, executable line of code, and the number of test cases. This is our experimental setup. That all the experiments are carried out on 64-bit Ubuntu machine with 8 GB RAM, and all the programs are written in NCC, and they have compiled in GCC compiler. And for getting the statement coverage, we have used gcurve. Gcurve is a utility tool coming with GNU compiler, and we have also used Minu to generate the mutants. And for statistic analysis, we have used understand C, that we will see in our further methods that what is the use of this understand C and all. And I have also mentioned the links of these tools here. Now when we have observed the result, like this is a line plot which shows the effectiveness of FTFL and D star, which is a state of the art fault localization technique. So we can see in the line graph where the x-axis is showing the number of statements examined, and y-axis is showing that by examining like this percent of statements, how many faulty versions are getting localized. So we can see this blue line FTFL is above this green and black line, which means that our method is outperforming. Okay, similarly, we have also presented the effectiveness of FTFL and compared with RBFN for Siemens tool, and we can observe that for each and every program point, our method is performing more effectively than RBFN. We have also compared the relative improvement using FTFL over existing techniques like Templar, D-Star, Cluster, OKI, IBF and BPNN for the programs in like SIR repository, and we observed that FTFL requires 34.61 percentage of less code examination than existing FL methods, and but but the problem with FTFL is that even though we have increased the effectiveness, but it suffers with the problem of ties and it is less effective for large size programs. So to get rid of this problem, we have defined hierarchical method for fault localization where we have first localized the bug at function level, and then we have selected the top suspicious functions like top k suspicious functions, and then we have dig the bug at those statements involved in those k suspicious functions only. Initially we thought of using only the like function coverage information to rank the functions, but we get to know that this method or this feature is not efficient enough, not effective enough. So we have moved towards another two. We have suppose two different features like function execution ratio, which shows the number of statements executed for a function for a given test case divided by the total number of statements available in that particular functions. And for computing the function complexity, we have to consider this uh, six complexity matrix where the number of executable statements present, total number of paths, cyclomatic, modified, strict cyclomatic, and maximum level of nesting. So we have then normalized each of these like complexity metrics using mean max normalization, and we have computed the like final complexity of that function using the equation A. Then we have generated the input matrix where we have used this function execution ratio and function complexity metric for each of the functions, and using this input matrix we have trained our network where the weight matrix for the first hidden layer is like this, and this is our proposed model where we are like connecting these two values, two features of particular function with the respective that neuron only, and the other connections we are keeping them as a zero. Okay, but we know that when the neural network will train and it will backpropagate, it will definitely assign some values to it. So now we have modified our objective functions. Like now our objective function is not to reduce the error only, but our modified objective function is to minimize these weights also. Okay, so then we have trained our network using this algorithm. We have computed the top k function which helps to define the knee, and based on the knee we have taken the top k functions, and then the statements involved in those k functions, we have taken the statement coverage of those statements and train other network, and then use the other virtual metrics to get the suspiciousness of those statements. This is the result where we can see that our technique of hierarchical fault localization able to remove at least half of the total search space. And this is the result using BPN and DNN and other like techniques. And this is our final result where we can observe that our method is 30% to 50% more effective as compared to existing techniques, and deep high deep that our proposed hierarchical deep neural network based method assign unique suspiciousness score to each of the statements. Now, for multiple fault localization in this method, we have classified the test cases into different fault focusing clusters, and then we have used each of the cluster to localize the bug using our method of clustering. So this is the result where we can see that we are outperforming. Now coming to our third approach, that is FDGFL, which is like function dependency graph based fault localization. Sometimes we can see that the function execution is the same for different functions. So to get rid of this problem, we have defined function dependency graph where we have captured the dependency relation between different functions. So in the function dependency graph, like these are the functions and these are the dependency relations. So we have the dependency is based upon the global variables as well as the function argument passing. Okay, so based upon this function dependency graph, we have defined two methods. Like first we have tried to use the existing SBFL techniques with FDG, and second one is we have trained the like value of in like executed edges with like neural network. Okay, so these are the notations we have used. So in our first SBFN method, we have used two different edge scoring method. If the statement or if particular edge in the function graph is invoked by a past test case, then we use a hierarchical like heuristic constant WP, and we increase the value of that particular edge with WP pass. If it is invoked by a failed test case, and then we increment that edge value with W fail. And after executing all the test cases, we compute the weight of each edge using this like equation 21, and then we normalize the weight based upon the maximum attempt weight of the edges. Similarly, there is another method for edge scoring. Since we have less time, so I am not going in the details. And then after that, we calculated the fault propagation of a score of a function based upon the addition of all the incoming and outgoing edges based upon their scores, and then we have selected the top k functions, and we have used the existing d star and templar method for ranking the statements involved in that top k functions. So these are the results. We can observe that the for HWN method, the WP W pass value must lie between 1.01 to 1.5, and W fail can lie between 0.01 to 0.2. And for W fail in DSN, we have taken this range, and we can observe that like our methods are effectively able to localize a buggy function is 89.39% and 91.33% of faulty versions of programs in 30% of the prioritized list of functions. So these are the comparison with related work where we can see that HD star, like HW and D star and DS and D star is performing better than D star for in a Siemens program. Now instead of taking like any existing method, we have used the coverage information of those edges, and we train the network. Okay, and after training the network and getting value of all the edges, we have calculated the value of that function using this two method, the average weight of passing dependency weight, or either or the max of the weight of the dependency edges passing through that particular function. So based, and then we have calculated the results, and we observe that here also we are performing better. And this is the result for the overall comparison for FDMLN with D star. And then we have used a similar method like multiple fault localization using FDMLNM. So here also we are using Kendall-Tau methods to find the correlations, and then clustering, and then taking top K 80% of the like top 15% of the statements involved in that top suspicious functions and all. And here we can see that FDMLNM requires 21.85 and 28.60 less code examination than D star and RBFL. Now coming to the fourth proposed work, EBFL. Since we know that any single method is not effective to localize or to get different type of bugs every time, so we have combined different domains of fault localization techniques, that is SBFL, mutation based fault localization technique, MBFL, and NNBFL, that is neural network based techniques. We have taken 11 methods from these different domains, and then we have used a voting method to determine whether the particular statement is buggy or not based upon the median of that particular rank. And based upon this voting, if the like if more than five technique will say that the statement is buggy, then we classify the statement as suspicious, otherwise we classify that statement as a non-suspicious, and then we do the score normalization of the statements in the suspicious class, because the values of suspicious is score given by different methods are in different range. So we have combined, we have done score normalization, and then we have used a ranking learning to rank method to combine the scores generated by different ranks, and we generated the prioritizers of suspicious functions. So these are the methods that we have used in this, and we can see like the on average, there are 42.19% of statements which are present in suspicious class, whereas 57.80 statements present in this non-suspicious class. That means we have reduced our search space in like at least half of the search space we have eliminated. There is the effectiveness of EBFL over DSR and Tantler for Siemens suit, and with CNN and DN for Siemens suit, and we are performing better in both the cases. This is the overall result with a comparison of like different methods: FTFL, high D, PD star, high ML, and EBFL, and we can see like we are performing increasingly better. So now I would like to conclude like we presented a Fisher test-based statistical technique for false localization using statement coverage and text execution result, and our method requires 34.61 percentage of less code examination than existing techniques. And subsequently, we have also discussed two hierarchical approaches for false localization, where our techniques are able to reduce the search space at least 50% of the time. And we have finally also defined or discussed the ensemble of different fault localization techniques, that is EBFL, which classifies the statements into different classes of suspicious and non-suspicious, and our proposed EBFL method performs on an average 58% more effective than existing FL techniques and 16.95% better than the existing proposed techniques FTFL, HID, FDMLN, and DD star. And these are the journal publications we got from this like works conference publications. These are the references we have used. Thank you so much.